Welcome to the last lecture in this series. Today I'm going to talk about some different applications in probing quantum materials. It'll be a little bit of a shorter lecture because I didn't want to dig deep into too many applications or cast too wide a net and just end up losing everyone's attention. So I ended up focusing mainly on 2D materials, partly because that's a lot of what comes through my lab, and partly so that the lecture would have some coherence and not just be a scattering of applications all over the place. All right. So quantum materials ends up being a very broad term. So as I went looking for applications to talk about, I found a Nature Physics editorial arguing on why the term quantum materials is relevant and a good term. So on sort of a trivial level, you know, all materials exist due to quantum mechanics, and quantum materials does sound like a trendy buzzword, but the term quantum materials, it spans a wide range of our traditional silos of knowledge, our traditional silos of departments in a university. So it spans chemistry and physics and materials science. To name a few, there's a big helping of math in terms of the group theory and the linear algebra, as we saw. So it's a good term to sort of bring things together from different disciplines. All right. So just as a quick review on how 2D materials started. The idea was you take a piece of graphite, and graphite is made up of these layers of carbon. And if you take a piece of tape and you put it together and peel it apart and do this repeatedly, you'll eventually end up thinning the graphite down to a single layer of carbon, which is called graphene. So this was sort of the birth of this whole 2D materials area of research. It's easy to say, you just take Scotch tape and you unfold it like that, and then you suddenly have graphene. There's a bit of an art in terms of actually making it and figuring out where you actually generated single layer graphene or single layer MOS2 or single layer tungsten diselenide, or you know, there's quite a family of 2D materials now that are often made by this mechanical exfoliation technique. Clearly, this is not very scalable for like industrial applications. So people are working on figuring out how to grow 2D materials with chemical vapor deposition techniques and things like that. But for now, most of the research is still done on these mechanically exfoliated flakes because they give you the highest quality material in general. But if we zoom in on that image of the graphene, it's this little smudge that's barely visible in an optical microscope that is actually the single layer graphene. All right, so the people who have spent a long time staring at these through microscopes can often have some intuition and make reasonable guesses on if it's single layer or bilayer just by looking at it, but it's certainly not a very satisfying, oh, I squinted at it and I think it's single layer. Especially if you're going to do a lot of processing to make a device or something, you want to be sure that it's actually single layer. So we talked about Raman spectroscopy a couple lectures ago. So for most of the 2D materials, there is a signature in the Raman spectrum. So As a reminder, the Raman is looking at vibrational motions. The different layers will interact with each other and change the vibrational motion of the sample. And that shows up in the Raman spectrum. So in the specific case of graphene, the signature is looking at the ratio of the intensity of the 2D peak, which is around 2,700 wave numbers, and the G peak, which is around 1,550 wave numbers. So for one layer of graphene, the 2D should be at least twice as high as the G peak, as can be seen in the yellow trace on top. For bilayer graphene, the 2D peak and the G peak are usually around ratio of 1. They're about equal intensities. And then once you get beyond 2 layers, it looks very much like the bulk graphite spectra, where the G peak is much more intense than the 2D peak. So here's a clean method to actually say, yes, that little smudge I can see through the microscope really is single layer graphene and not 2-layer graphene. So Raman ends up being quite sensitive to exactly how the atoms are arranged. We want to be able to look as directly as we can at the crystal structure and understand what the crystal structure is of our material and how it's oriented, because those will determine their optical and electronic properties. And it's those electronic properties that we're going to try to use to make new devices and see new quantum phenomenon emerging. So graphene can be rolled into different types of carbon nanotubes. Nanotubes went out of fashion, and they seem to be maybe inching back into fashion as people get better at manipulating nanomaterials. So the SWCNT is a single-walled carbon nanotube, and then the single-walled carbon nanotubes can come in semiconducting, metallic, and insulating versions. So depending on how the nanotube gets rolled up, so in the top right corner, there are 3 different carbon nanotubes. They all cartoons of 3 different carbon nanotubes. They all look the same if you're not looking closely, but highlighted in gray, it shows the repeating order. And this is this change in exactly how it's rolled up will change its Raman modes. It'll change its vibrational modes, which we can see in the Raman spectra I pulled. So whether it's a semiconducting single-walled nanotube or a metallic single-walled nanotube, that's reflected in the Raman spectra. But it's a little bit amazing that you take all the exact same atoms, they're bonded very similarly, they make a very similar shape, and still you get dramatically different electronic properties. So there's a lot of subtlety to how the material is put together and how that's going to affect the properties that we're going to try to make use of as we create things. So having a good measure, having a good feel for exactly what the properties are, how the atoms are arranged, will define whether you're going to have a successful experiment or it's never going to work. So certainly Raman is very powerful in terms of being able to probe these, how the molecules are arranged, how the atoms are arranged, and give you some feedback on if the material is going to be worthwhile pursuing further experiments with or not. So why do people care so much about having single layer materials? Well, it restricts our geometry to largely 2 dimensions. So when we talked in group theory, it was all about symmetry. So a 2D material has different symmetry than a 3-dimensional material. And so this will change some of its properties. And here is the band structures. So if you remember, the lines on the bottom in the band structure are the valence bands, and the lines on the top are the conduction bands. All these TMDs, as they're drawn, are semiconducting. So the difference between the semiconductor and the insulator was how big this band gap is, how big an energy difference is between the top of the valence band and the bottom of the conduction band. So insulators have very large gaps. Semiconductors have gaps that can be transitioned reasonably easily, and metals have no gap. The valence band and the conduction bands end up overlapping. But what's interesting here is for MOS2, WS2, MOSE2, and WSE2, for monolayers, they're all a direct band gap, which means that the top of the valence band is directly below the bottom of the conduction band when drawn out in momentum space. So remember, the y-axis is energy and the x-axis is momentum. As soon as you go to 2 layers and above, we end up with indirect band gaps. So if you're trying to do optical probing or something, you suddenly go from, in the direct band gap, you can just couple a photon directly into an electronic transition. For indirect band gaps, you need to couple in a phonon also. So you need a phonon to move the system in momentum space coupled in with the photon to move it in energy space, which becomes a much less likely phenomenon to occur. So it's interesting how just thinning the material changes the band structure so dramatically. So really being sure that you have single layer if you're trying to do some sort of device is key. But there's some interesting twists. This was an experiment that was done by a UConn student actually in my lab. And this is images from his thesis. He was looking at tungsten diselenide, one of the materials, but he had a bilayer system. So it should have been an indirect band gap. But he found that when you applied uniaxial strain, so he made a jig so he could put the flake he was interested in under a controlled amount of strain under the Raman microscope. Actually, here he's looking at photoluminescence intensity. The Raman microscope will measure Raman spectra and photoluminescence spectra. So when he put it under strain, he saw the photoluminescence go from this fairly weak red line, and it was dramatically enhanced through to the purple line when he applied 3.6% strain. And that enhancement of the photoluminescence and the shift in the peak position meant he was going from an indirect band gap to a direct band gap. So the indirect band gap is much less likely to get a luminescent transition. So that's why it's much dimmer. The direct band gap, you're much more likely to have that photoluminescence emission. So that's why the intensity is much stronger. If we look at his modeled band structure, the red lines are the indirect band gaps. So the lowest position in the conduction band is offset in momentum space from the highest position in the valence band. But if we look at the purple traces on the band diagram, we can see that by applying the strain, it's ended up lowering that band structure. So now it's a direct band gap material. If we go back to thinking about how a lot of these materials are being formed. We're taking Scotch tape and we're just ripping material apart. So it doesn't seem that unreasonable that you could certainly induce strain in the flakes as you rip them apart and then transfer them between substrates and things like that. So being aware of the strain and the possible sources of strain and how to alleviate the strain, because the strain is going to change the crystal structure. And the crystal structure is going to, the change in the crystal structure is going to change the band diagrams. And we're trying to use the band diagrams and the band structure of the material to get new phenomenon to occur, to make useful devices and things like that. So it's, there's a whole area called strain engineering, which has been used to make some classical semiconductor devices run faster. But in the 2D materials world, it is something to pay attention to, like why one flake will work and one won't. It could be due to some strain that was accidentally induced in the material as it was exfoliated or transferred between the tape and the substrate, or as we'll see in a moment, as it was transferred to stack things. So again, Raman could be used to map out the strain in a sample to see exactly where the strain is, how much there is, because if we think of Raman again as the vibrational motion, if we think of it as a system of balls on springs, the strain is going to change the spring constant. It's going to have the spring either it's slightly pulled apart or slightly compressed. And so that will change the Raman spectra, which would be a direct readout on where you are in terms of strain on the material and whether that flake is useful to proceed with or not. So it's interesting to get these one layer materials, but there's a limit in how much you can tinker with the material to get the properties that you're actually looking for. You need another degree of freedom. So in bulk semiconductors, they usually dope the materials, and they dope it in different ways to change the band gaps and band structures to get the properties they want. In these exfoliated materials, it's really hard to dope. Lots of people are still trying, but it's non-trivial synthetic inorganic chemistry to break bonds and stick in defects on purpose at specific locations, at specific densities to get properties that you're interested in a reliable, repeatable way. So one interesting way that people have been trying to engineer the band gaps to get new properties, new interesting things, is to start stacking these 2D materials. So these are called bilayers, and if you stack them at different angles, they're called twisted bilayers. So we're moving the crystal orientation relative to each other. So in the image on the bottom, there's the red lattice and the blue lattice, and if we stack them on top of each other, we see that there's suddenly a sort of funny hexagonal pattern that appears, and that's the interference between the two patterns. And those are referred to as moire patterns, moire fringes. They're sometimes used in optical illusions, but they're real, and we'll get changes in the electronic structure of the material based on the interactions of the two layers. So if we go back 2 slides, one layer was going from 1 layer to 2 layers, changed the band structure dramatically as the 2 layers interacted. And by controlling the angle at which they interact, we can control the spacing in these moire patterns, and we can get new band structures to appear. So often people are trying to make flat band regions. And here, they stack two tungsten diselenide flakes on top of each other, and they've offset the K and K prime values in the band structure a little bit from each other, but just enough that they overlap still. And so you end up with these broader, flatter bands than would be in a normal bilayer. So by introducing some twist, we have another degree of freedom that we can start to engineer our band structures. And as we engineer our band structures, we can get new phenomenon to occur, new interesting things to happen. So if we're going to take two layers and we're going to try to stack them, and we're going to try to control the orientation relative to each other, we better know what the orientation is of the first flake before we try to transfer it onto the second flake. So polarized second harmonic generation, I think I've shown this image before, is one of the ways people are doing it. So here, this particular image is MOS2, and MOS2 happens to grow in these nice triangular flakes. So you can do some transferring just on the flake shapes and get some stacking like you expect, but a lot of other 2D materials don't have these nice triangular shapes. They don't have a nice crystal orientation facets that show you which direction you're going. So you need to actually measure which direction the crystal is. So in polarized second harmonic generation, we bring in a photon of we bring in two infrared photons, and we get back one blue photon. So the infrared photons have frequency omega, the photons coming back have frequency 2 omega. And this, due to symmetry, is only allowed in monolayers or broken inversion symmetry materials. So for the rotated materials, you'd still have second harmonic generation. But if we control the polarization of light, and remember that the polarization of light is the direction of the electric field. So the direction of the electric field will interact with the different crystal directions differently. If we look at the little cartoon of the crystal, we see there are some directions, the bonds are anisotropic. It's not exactly the same in all directions. There's one direction where we lined up all the yellow balls. There's one direction where they're offset from each other. So the intensity of the second harmonic will vary with crystal orientation. And as we rotate the polarization and keep track of the intensity of the second harmonic, we can map out the flake crystal orientation relative to the macroscopic shapes that we can see. So that's what the bottom figures are showing. And so once you know the crystal orientations, then you can go and stack the materials at different angles to give you these moire patterns, which can be useful. This could also be done with polarized Raman measurements. The challenge with the polarized Raman measurements is that the different Raman modes will have different symmetries. So here's an example using germanium selenide, a different 2D material. But we talked about the character tables and the A modes and the B modes. The G just means it's symmetric. It's from German for gerade, which means even. But you can see that the different Raman modes all have different patterns in the polar plot. And that's because they're along different motions of the molecules that are in the 2D flake. The different motions of the atoms are going to give us different symmetries. So the polarized Raman, you need to make sure you're looking at the mode you think you're looking at. So you need to do good peak assignments and really understand what the different symmetries are for your material. So I think that's why the polarized SHG is a little more popular because you don't have to think quite as hard. It's just you have the intensity of the second harmonic and you map that out. Here you have to think a little harder about which mode you're looking at and how that should transform as you rotate the polarization. But both would be valid ways of figuring out your crystal orientation before you start going to make van der Waals heterostructures or van der Waals twisted bilayers. So one of the papers that really set off this twisted bilayer research was when a group at MIT found this superconducting in the twisted graphene bilayer. So it had been predicted theoretically a while ago, I think back in the 90s, although I may have that date wrong. But it wasn't proved. Just manipulating materials at this accuracy, the techniques weren't developed for it until the last couple of years. But having the two graphene layers twisted at this magic angle of 1.1 degrees meant that they could suddenly get superconductivity in this device. So there's a picture of the actual device itself. There's a cartoon of it. By applying a voltage bias, and then this was done at low temperatures, but by applying a voltage bias, they can control the carrier density and the right carrier density regime. So the right number of states filled by electrons, you can get superconductivity. So superconductivity is when resistance drops to zero. It's a very quantum mechanical effect. But what struck me less about the paper was the superconductivity was what made the headlines, but it's intriguing that they can easily tune the device between the Mott state, the Mott insulator state. So it can be an insulator, it can be a superconductor, it can be a metal. So by moving the band structures and then tuning the carrier density, we can switch things from a superconducting state to an insulating state, which seems quite wild. So there's these wildly different electrical properties as we fine tune the different parameters in the system. So we can tune it to be a metal conducts electricity, and it obeys Ohm's law, where the voltage is equal to the current times the resistance. It can be tuned into a superconductive state, where the resistance of the electrical current drops to zero. And the electrons form what are called Cooper pairs. So Cooper pairs are a composite boson. If an electron, as we talked about, is a class of particles called a fermion, it has a spin 1/2, plus 1/2, minus 1/2. And fermions can't be in the same quantum state. Bosons have integer spins, so they have spin 0, spin 1, usually some integer, and then bosons are allowed to all be in the same quantum state. So if we take two spin 1/2 particles though, 1/2 plus 1/2 equals 1, or 1/2 plus minus 1/2 equals 0. So if they're paired up in this state that's called a Cooper pair, they suddenly become a boson particle rather than a fermion particle. And then as a boson, they can all exist in the same quantum state. And this is where we get the superconductivity. It's really a superfluid of these Cooper pairs. The Mott insulator is a different interaction. It's also due to electron interactions, but it's when we have just one electron per site filling the lower band. So we end up splitting the bands just a little bit, and one electron per site is filling the lower band, and then the upper band remains empty. And having bands where the bottom is full and the top and the upper band is empty is sort of the definition of an insulator. And it happens just in a certain carrier density range when we filled all of one set of sites. And for anything to move around, it would have to either jump in energy or flip its spin, or so it doesn't want to do that. So it ends up being in this insulating state in between metal states. And then if we added more electrons, then the extra electrons would start filling in those upper bands, and it would go back to a conductive state. Another interesting quasi-particle, composite boson particle is called an exoton. So exotons are electrons and hole pairs. And so when we excite an electron from the conduction band, from the valence band to the conduction band, we leave behind a net positive charge. We can think of that net positive charge that's left behind as its own particle that is referred to as a hole. But of course, a positive charge and an electrical charge, negative charge have electrostatic attraction to each other. So we can have a plus state and a minus state, and they can be bound due to electrostatic interactions. And then this new particle, the electron has a spin 1/2, and the hole also has spin 1/2. So then we end up again with this composite boson particle that can do all the things that bosons can do. One of the things that bosons can do is they can condense into this Bose-Einstein condensate, and it's where they all end up in the exact same quantum state. And so one wave function can describe them all, and that wave function actually ends up being macroscopic in length, which is really wild to think about. So the observation of Bose-Einstein condensate won the Nobel Prize in 2001. So it was one looking in these very dilute, very cold ions. But now it's the paper I think is from last year, from 2019. They observed exoton Bose-Einstein condensate at 100K. So instead of trying to get your ions in your magneto-optical trap cooled down to 0.1 Kelvin, 0.01 Kelvin, I forget what the numbers were, but it was, they pulled out every trick they could to get it as cold as possible to get the Bose-Einstein condensate. Now, 100 Kelvin is quite easily achieved. Liquid nitrogen will get you down to 77 Kelvin. And liquid nitrogen is basically just air that's been cooled off to the point where it's a liquid. So these exotons are this other composite boson particle, and trying to tune them in stacked heterostructures. Here they stacked tungsten diselenide and molybdenum diselenide. And when they do that, if we look at the band structure on the far right, we see there's an offset between the between the bottom of the conduction band and the top of the valence band in momentum space. So you can actually get this exoton bound between the conduction band in the molybdenum diselenide and the valence band in the tungsten diselenide. And then because it's bound across this momentum space, it becomes much longer lived, just because then you have to couple into a phonon to get back and have the electron and hole recombine. So the exotons are quasi-stable. They will eventually recombine and usually emit a photon, which is how you read out that they've been made. There's also a quasi-particle called a trion, which is 3 particles, either 2 electrons in a hole or 2 holes and an electron bound. And those 3 particles are bound together called a trion, and there's a different emission spectra for that. But yeah, so now that we've taken our one-dimensional material and we've stacked it in specific ways, we can actually get at very interesting quantum physics showing up at much more accessible temperatures. Another way people are thinking about the band structures and how to utilize them in these 2D materials is called, it's labeled Valtronics. So again, if we look at the band structure, so there's the 3-dimensional representation on the left, there's the 2D representation on the right, which is a little easier to think about sometimes, at least for me. We'll see that here, the way the tungsten diselenide was prepared, it was in an indirect band gap state. And at the gamma point is where there would be a transition with no phonon. But there's the K and the K prime valleys. Those are the valleys in the conduction band. So that's where the electron is going to settle to in the conduction band. And it turns out, due to conservation of momentum, we can actually address the 2 different valleys individually using either left circularly polarized light or right circularly polarized light. So at the top, I have some cartoons showing left and right circularly polarized light. And it basically depends, as you're observing the light, which direction does the electric field rotate as you sit at one spot? Does it rotate to the right or does it rotate to the left? But that rotation contains some momentum. That momentum allows you to directly address either the K valley or the K prime valley. And then the photon that's emitted from the K valley or the K prime valley will also be polarized in a specific way. You end up either left polarized coming out or right polarized coming out, depending which valley it coupled out of. And so it's a different approach to using the quantum band structure of the material to store information. You can store it in the K or the K prime valley, and you can write into the K or K prime valley, and you can read out from the K and the K prime valley. So that's another way people are thinking of how to use the band structures and take advantage of the band structures to do interesting things. All right. And then as I was looking for examples, I found this last example that I thought was really cool. So this is actually moving away from 2D materials, but it's using what's called the magneto-optical Kerr effect. And basically, if you take light and you linearly polarize it, so the direction of the electric field is always the same relative to the sample, and you send it down through a polarized beam splitter through a microscope and look at the reflected light, send it back through the polarized beam splitter, and then cross your analyzer. So only certain polarization of light gets through. You end up with contrast in the magnetic domains. So the magnetic field of the materials will change the polarization of light a little bit. It's a very slight effect, but it's enough to be measurable. And so there's a nice picture of magnetic domains, which are the basis of our hard drives, basically reading and writing the magnetic domains, but they can actually be visualized in a microscope. And here's a nice picture of it. So the quantum mechanical part, well, one area that's starting to be explored for quantum materials is magnetic Skermions. So there are these small swirling topological defects in the magnetic fields of the material, the magnetic domains. And their stabilization and dynamics are highly dependent on the topological properties of the material. So they're often found in non-centrosymmetric magnetic compounds or in thin films with broken inversion symmetry. So going back to thinking about group theory and how the symmetry of the material changes its properties. But these Skermions can behave like particles. They can be created and annihilated, and it makes them suitable for thinking about how to use them for information storage or logic or things like that. And they can be quite small. But I found this nice movie of the Skermions being formed. So the little dark dots are the Skermions. The long black lines are more traditional magnetic domains, but you can see how they set up a system to sort of generate Skermions in a almost microfluidic device. It's not really microfluidic. This is all magnetized material, and they're shifting the magnetic field to make these new magnetic domains. But I thought it was a really nice visualization of quantum materials and probing quantum materials, and sort of to end the lecture series on. So my conclusions are the crystal structures and the crystal defects are really important in understanding quantum materials. All the material properties that we try to make use of come out of the crystal structures and the defects in the crystal structures. And there's lots of different possible light matter interactions, and really thinking about how the light and the matter interact is important for characterizing the quantum materials and going in and probing the quantum materials, storing information, reading out information from the quantum materials. Involves thinking about this light matter action fairly deeply. So thank you for your attention. I thought I'd keep it a little shorter, so that's what I have today. I'm happy to take any questions.
Thank you, Arthur. I just want to say, we really appreciate all of the effort you put into the class. And I personally learned a lot. I know my students have benefited, my interns have benefited greatly from your explanation of things that I struggle to explain. And you've given us a lot to chew on. So I don't have any questions, but I just wanted to say thank you very much. But if anyone else has any questions.
I just also wanted to thank Arthur. This has been really eye-opening and a good experience.
Thank you so much. Thank you, Tina, for organizing this and giving me the opportunity. And thank you, Carol, for all your wonderful feedback on different things.
Bye-bye.
Bye.
Arthur, I'm looking forward to the next thing we do. Ha-ha.
Sounds good.
Okay, I'll be in touch.
Sounds great. All right.
Bye-bye.
Have a good day.